Hello students, I welcome you all for this particular lecture. So in previous uh, lecture we have seen the design procedure of tension members, the steps I was mentioned there. So in this particular lecture I will be solving one design problem so you can understand the procedure given earlier. The design problem given here as design a tension member to carry a factored load of 340 kilonewton. Use M20 bolts of property class 4.6. The gusset plate is 8 thick. Use single angle for the member. So this is the design problem given. Here the load is given, that is the factor load is given. Then the diameter of bolt is given. Then the property class of bolt is 4.6 is given. The gusset plate is given. First you need to write the given data. Here the given data are being written. All the data are given here. Then solve step number 1. The step number 1, this is step number 1. Step 1, so preliminary selection of section. First section is preliminary selection of section. So you have to select a preliminary section. So you have to use the formula TDZ AZ into Fy divided by gamma MO. So from this formula you get AZ. AZ will be TDZ into gamma MO divided by Fy. TDZ is 340, that is factored load, into 1.1 divided by 250. You get a area 1496 millimeter square. So this much is required area, but according to the uh, code, so you have to increase this area by 20%. Increase this area by 20% as factor of safety. After increasing area you will get 1795 millimeter square. 1795 millimeter square. You increase the area by 20%, there is as a factor of safety, or you may increase the area by 25%, as I mentioned in procedure, 25 to 40%. So let us take here is a 20% increase in area. Then for this increased area you just refer steel table, which section will give you the uh, area here. So here just refer the steel table. In this steel table just is equal angle sections, rolled steel equal angle sections, but in the problem given provide single angle section for the member. So you have to choose a single angles. So here which section will be giving you this much of area, just check it out in a steel table, which section provides this much of area or higher than this one. It should not be lesser than this one, you should select higher than this one only. If the section getting the same area, then select that area itself. So here I'll be searching, and I may get probably 100 by 100 by 10 gives you the area, that is 100 by 100 by 10, 19.03. And other angles some giving you the lesser than that, or very higher areas. So it is almost nearer to that area, that is 100 by 100 by 10, that is 19.03, that is 1903 angle will be giving. So hence from steel table select ISA 100 by 100 by 10 mm. So area provided, then this angle we are choosing, the area of this angle will be 1903 millimeter square, which is more than 1795. So okay, or nearer equal to this much. If you're getting this much area of any section, you can choose that section also, or else more than that one which is nearer to that. Then next you have to calculate, after area you have to calculate number of bolts required. Number of bolts required, that is n equal to load divided by bolt value. So this is the formula. Then the bolt value we have to calculate. Bolt value will be the least of strength of bolt in shearing and bearing. So you have to calculate shearing strength and bearing strength, because the property these bolts given here, ordinary bolts of property class 4.6. so the least strength of bolts in shearing and bearing will be the bolt value. So let us calculate strength in shearing. Strength in shear, so the formula is, we have a VDSB FU divided by root 3 this gamma MB into bracket NN plus NSASB. This formula we know, we have solved many problems in bolted connections. You know how to take NN and NS here. Since the angle connected to the gusset plate here is like this is the gusset plate, the angle connected here is like this, single angle, and here is the bolting. So this will be single shear. Here you will get only one shear, so you have to get a single shear here. So when you substitute all the values here, let us take uh, ns equal to 1 here, ns equal to 1 and nn equal to 0 here, assuming uh, the shank portion shears are intercepting the uh, shear plane, shank portion intercepting the shear plane. Here we have taken ns equal to 1. Then when you substitute all the values, that is 400 divided by root 3, gamma mb is 1.25 into this one 0 plus 1 into area is pi by 4, d square is 20 diameter bolts given, you will get 58.04 kilonewton. This is shear strength of the bolt, it is single shear. Similarly calculate second strength in bearing. Strength in bearing, that is VDPB, strength in bearing. We know the formula, VDPB is equal to 2.5 kb d into t fu divided by gamma mb, where kb is the least of e by this one second, p by this one minus 0.25. You will get this in a code, refer code book, FUB by FUP and 1. So here minimum edge distance to be taken. So minimum edge distance, just take a minimum edge distance, minimum E to be taken 1.7 times of diameter of hole, then you will get E equal to uh, approximately to 40 mm. E will get, then pitch to be taken 2.5 times of D, that you will get 50 mm approximately. Just to calculate minimum edge distance and the pitch distance, then calculate that one. You will be getting first value 0.99909, then 0.507, then 0.975, then you will get this one. Then the least value will be the kb, therefore kb equal to 0.507. 0.507. 0.507 kb. Okay, so this E and P will not be given, so you have to calculate the minimum values for. Okay, so minimum value, how much to be taken, edge distance and pitch distance, all are given in a code book. So please refer a code and get the minimum values. So after this one, then substitute all the values in VDPB. You will get the VDPB. You will get 2.5 into 0.507 kb value into 20 into thickness 8. Why thickness 8 is the least value of gusset and angle. So angle thickness is 10 mm, gusset plate thickness is 8 mm. To take the least thickness into 410 divided by 1.25. Okay. Then VDPB will be, you'll get 64.89 kilonewton. Therefore bolt value will be the least one, 58.04 kilonewton. This is the bolt value we get. Now calculate number of bolts required. Number of bolts required, N equal to, we have a 340 kilonewton, then 58.04. 340 is a given load, divided by this one, you will get 5.85, say approximately 6 number of bolts required. Then after calculating number of bolts, arrange these bolts. So to arrange the bolts, so let us draw here. This is angle section. Five number of bolts to be arranged. 1, 2, 3, 4, sorry, 6 numbers, 5 and 6. This is the arrangement. This is the gusset plate, and draw a section also here. I'll draw a section. Here the bolting is done. The bolting. Then also mark the pitch distances. And edge distance. Edge distance we calculated as a 40, pitch as 50, 50, 50, 50 and 50 here. And also refer steel table and mark EXX and CXX. This will be CXX and this is EXX. So refer steel table and get CXX and EXX. You just refer it and here given center of gravity cxx, and also given distance of extreme fiber exx. So refer it for this angle section 100 by this one, for 100 by 100 by 10. So what is exx and cxx? So from the steel table you will get exx will be 71.6 mm and cxx 28.4 mm. So okay, for this angle section, this is for ISA 100 by 100 by 10 mm. So from steel table you will get these datas. So mark on this figure, so cxx and exx, which represent the centroid of the bolts as well as the distance of extreme fiber of the angle sections. So this the heel section, and this is the toe sections, and this also toe section. Okay, so after this, so we need to calculate the strength, or we need to check this one, that is the tensile strength of the assigned section. So the tensile strength of the assigned section, as we know, the strength of the section will be the least of the strength of the section. The strength of the section needs to be checked. So once you assign the number of bolts, or arrange the bolts in a chain pattern, and your this angle section is ISA 100 by 100 by 10, and this assigned section, whether it is safe or not, we need to check. The strength governs, that is three things you need to check, that is TDZ, TDN and TDB. So the least of three, or this whatever TDZ, TDN, TDB we calculate, these should be more than the factored load given. Should be more than the factored load given, then only we call it as a safe. If suppose they are coming less than this one, you have to revise the section, then once again you have to redesign it. Okay, then the next part will be analysis part. So we need to analyze analysis part. Let us calculate first one, strength due to gross section yielding. So that is TDZ we need to calculate. So TDZ will be AZ into Fy gamma m. AZ you need to write the provided area, that is 1903 into 250 divided by 1.1. You get 432.5 kilonewton, which is more than 340 kilonewton. This 340 is a given load, so safe. Second one, strength due to net section rupture, that is TDN. So we know the formula TDN, refer code. So just write the formula, that is 0.9 ANC Fu divided by gamma ml plus beta A0 into Fy divided by gamma mu. Okay, so you know how to get ANC or A0. ANC is what? Connected leg area, AGO is what? Outstanding leg area. Here the leg connected here is this 100. This is 100. This is equal angle only. This is also 100. Okay. So the connected leg area needs to be calculated here. So how much it comes? Connected leg. You know how to calculate the connected. 100 minus, that is thickness is 10. 10 by 2 minus 1 diameter hole, 1 bolt, minus 22. Minus 22. You will be getting into 10. 730 millimeter square you get. Similarly, outstanding leg area, this leg area, outstanding leg area, 100 minus 10 by 2 into 10, you will get 950 millimeter square. So these all things you know already because we have solved a few problems. You know how to calculate ANC and AGO. Then you calculate beta, that is correction factor beta, 1.4 minus 0.076 into W by T, then Fy by Fu, then Bs by LC. This should be less than or equal to 0.9 Fu by Fy gamma ml by gamma mo by gamma ml, and it should be greater than or equal to 0.7. Fu by Fy gamma mo by gamma ml should be greater than or equal to 0.7. Then W is what? Outstanding leg width. Here W is outstanding leg width, this one, outstanding leg width, that is 100. Thickness of the angle is 10 mm. Then Fy is 250. Then Bs, shear leg width, that is W plus Wi minus T as per the code. Here we get a shear leg width as Bs equal to W is this one, then Wi will be up to here. So Wi means 100 plus Wi means Cxx. Cxx is 28.4 minus thickness 10. You get this one. So you'll get 118.4 mm. That is 118.4 mm. This is this. Then LC will be this one. LC will be from here, from the first bolt hole center to the last bolt hole center. LC. Then LC will be how many pitches here? Yes. Okay, LC 1, 2, 3, 4, 5. 5 into 50. 5 into 50, you will get 250 mm LC. Okay, LC will be the length of the end connection measured from center of the first bolt hole to the center of the last bolt hole. This is LC. Length measured along the direction of load, center of the first bolt hole to the center of the last bolt hole. Okay, substituting all values in above equation, we get TDN. We get a TDN as beta. First you calculate beta. When you substitute these all values, you will get beta as 1.180. This should be less than or equal to this value, and this should be greater than this value. Then substitute all in above TDN equation, we get TDN as 470.26 kilonewton, which is greater than 340 kilonewton. Again, it comes to be safer side. It is safe. Okay, this is TDN. Then next you calculate TDB. So TDB, that is the third one, block shear strength. Block shear strength, that is TDB. Again, we are having two formulas. You refer code. So you'll be getting TDB1 and TDB2. So TDB1 formula, we are having AVZ Fy divided by root 3 gamma MO, one term, plus 0.9 ATN Fu divided by gamma ml, one term. Then TDB2, 0.9 AVN Fu divided by root 3 gamma ml plus ATZ Fy divided by gamma MO. So these are the two formulas you are having. Write these two formulas and calculate the block shear strength. So here AVZ, AVN we need to calculate, ATZ, ATN. Okay, so here we need to calculate AVZ. AVZ means the shear area. Shear will be parallel to the load. Okay, so how it fails? So it may fail like this. It will be like this. The plate may come out like this, So shear area means from here to here, last center shear area. Then tension area, this is the tension area, that is LT. I hope you understood this one. This I explained in previous problems. This is shear area along the load. This is the load direction, this one. So this is the shear area. Then how to calculate this shear area? Shear area to be calculated LV into gross shear area into T. LV is how much? So this one LV will be, so the you have to calculate LV. Here LV you have to calculate 40 plus 5 into 50. Okay, so that is 40 plus 5 into 50. You get 290 mm. 290 mm. You get LV as a 290 mm. Then 290 multiply by thickness, you get 2900 millimeter square. Then AVN, that is detecting the holes. How many holes? 1 2 3 4 5 full holes. Then half of this one here, this one you'll get 5 number of bolt holes, 1 2 3 4 5, and this is half. So that is 290 minus 5.5 into 22 into 10. You'll get 1690 millimeter square. So similarly calculate ATZ means this area, that is the tension area. Tension area we are having LT is EXX distance, this distance EXX to be taken. from the center of bolt hole to the toe of the angle section. This much, this area is under tension. That is CXX is EXX is 71.6 into 10. You get 716 millimeter square. Then 18 is deducting the bolt hole, that is 71.6 minus 22 by 2, means half of the bolt hole is deducted. Half of the bolt hole into thickness, we get 606 mm square. Substituting all the values in TDB1 and TDB2, we get TDB1 as 559.41 kilonewton and TDB2 you get 450.7 kilonewton. So both are more than 340 kilonewton, hence safe. Okay, then finally you should write one line, hence the assigned section is safe in carrying the load. Hence the assigned section is safe in carrying the load. That is ISA 100 by 100 by 10 is safe in carrying the load. Okay, so this is the